Hello everyone, welcome to lecture 3 of the Gyan course. As every day, I'll briefly recap some of the things that we discussed in the previous lecture and then continue with the topic. So, in the previous lecture, we discussed the basic ideas behind X-ray CT and ultrasound positron emission tomography PET and MRI. So those were the key like the ideas behind these technologies we discussed first, and then we looked at ray optics. Whenever you want to build instruments with light, you need to understand like the different models for light, and ray optics is perhaps the simplest of them. And there are a few simple postulates or basically the principles which are the assumptions of ray optics, and the key one being the Fermat's principle, which says that if light travels from point A to B, it takes the shortest time to go from A to B. Okay, and and everything is built. Ray optics is built on like the basic assumptions, these basic the postulates of this sort. Okay, so light rays travel along the path of least time. Okay, so today we'll switch gears a little bit and talk about wave optics. So there are some a set of phenomena which cannot be understood using ray optics. If you think of light as rays, then already understand a lot of things. But there are certain kinds of optical phenomena, for example, diffraction and interference, which don't make sense from the ray perspective, but make sense from the wave perspective. I'll get to exactly what is interference and so on in today's lecture. But this is that's the topic we'll be covering today. So we'll think of light as waves. Okay, and in the context of optics, wave optics is like so light. This is the entire range of the electromagnetic spectrum, and this is the visible region. This is really all the everything that we can see with our eyes is a very narrow sliver of the entire electromagnetic spectrum. This goes even farther on this side and farther higher, on this side as well. In fact, this side you have radio waves and so on. So, as you all probably know, like electromagnetic waves, even radio waves are electromagnetic waves. Light is an electromagnetic wave. Everything is an electromagnetic wave, and this is the electromagnetic spectrum. So, this is the visible region which our eyes can see, but we can use detectors of different sorts to see the infrared or see the ultraviolet and beyond. So it's because we understand how this works, all the principles that we first figured out for visible light can also be applied for infrared and ultraviolet or any wavelength range. Of course, you will have to build slightly different instruments and slightly different kind of lenses and mirrors and so on. But they like the principles are whatever we learn for visible light will also be applicable to most of the electromagnetic spectrum as well. So here is kind of an illustration of what. So previously we saw that all of light or optics can be understood in quantum optics using quantum optics as the most general theory of light. But that is too complicated for us to solve kind of problems in the real world, and therefore, so basically, we are using the simple like we can use wave optics as something which is a bit more complicated. It's so ray optics is a subset of wave optics. Okay, so wave optics is a little bit more complicated, but it incorporates everything that about ray optics is a subset of wave optics. Okay, so that's we will everything we will learn today can like sort of under some assumptions, under some simplifications, you can kind of figure out all the ideas of ray optics, whatever happens in ray optics, can be thought of as kind of can be derived from the equations and the things that we will learn today. But additionally, apart from everything in ray optics, it also explains a bunch of other phenomena which are very useful in practically building practical systems. Okay, so just like with the postulates of ray optics we discussed last time, we also have the postulates of wave optics. Okay, so again, some of them are similar to that of ray optics. So there is something called a refractive index. It is the speed of light in that particular medium. So basically, it's speed of light in free space divided by n, where n is the refractive index. So the speed of light in that medium is speed of light in air divided by n, and here is the refractive index. And typically, n is greater than 1 for some like most media. Okay, there are special materials called metamaterials where n can be like less than 1 or even 0. We will not, that's a topic for another discussion, but in like for most real world materials that we will encounter, n is greater than or equal to 1. Okay, then the second thing is there is such a thing as a wave function. Okay, so you might have heard this word wave function in the context of quantum optics or something of that sort. This is a simpler version of that, where basically um, it's it's a function u, which it's a function of space, 3-dimensional space x, y, z, and 1 dimension of time. Okay, so it's x, y, z, and time. Those are the different kind of variables, independent variables, and this function, like basically it changes from place to place, and over time it changes. That's really what this is saying. Okay, and it follows what's called the wave equation. This wave function follows this kind of a differential equation, where this del square or nabla square is basically partial derivatives along x, y, and z, second order derivatives. This is called the Laplacian operator. So I won't go into exactly how we derive things of like sort of how we go from the wave equation to actually the equation for a wave for now. But what I want to tell you is that the solutions exist, and like I'll show you what are the different type of solutions that are commonly used. And another principle of wave optics is what's called the principle of superposition, meaning if you have two waves in the same space, so they're going they they add add linearly to each other. Okay, they like if one wave is going in one direction, other wave is going in a different direction, the way like effective amplitude of the wave at any point or phase at any point, you can add the two waves and get the effective like wave properties at any point in space and time. So it's a simple linear addition of two waves, and this generalizes to n waves. Okay, those are the postulates. Additionally, you define a couple of important parameters: intensity and power. So intensity is basically the magnitude square. Magnitude, roughly speaking, it's the magnitude square of the field. Okay, and then the power is, that's a good question. We'll get back to that a little later. Okay, so the power P of t, there is an integral of the so how much power is there as a function of time. You integrate over the area or space, you get a function of time. And so if you integrate like so how much power is there which in that particular wave can be at any instant in time, can be integrate. If you integrate the intensity, you will get this number. Okay, so basically the wave function has some properties in space. It's traveling in space, And whenever you make a measurement of the, you cannot directly measure the wave function per se. All you can do is measure the intensity. So you can be there are several ways of thinking about intensity. One is that, say, if you think of, let's take the example of electromagnetic waves. So there is an electric field and a magnetic field which are traveling in space. Okay. Now the electric field, you cannot easily measure the electric field itself. You can measure the consequences of the electric field. The process of making a measurement requires that you measure the intensity, meaning you will not find E but magnitude of E squared. Okay, that's really the only quantity that you really are capable of measuring. That's what the experiments allow us to do. And so basically, like if you think of, so that's in fields. If you think of photons, photons have like are traveling in space, and when you make a measurement, the process of making a measurement means that the wave function becomes intensity like intense, which is magnitude squared. Okay, so all you can measure is this photon count or number of some sort, depending on the depending on this. So, and power is basically, it's kind of related to the, if you add up all the overall, it's kind of like the energy contained in the wave, how much of energy is there, and how it's changing as a function of time at a particular point, in a particular kind of area. Okay. So there are a few other things we define. So there is such a thing as a monochromatic wave. So when you have a wave, the wave kind of graphically looks something like this. So it has a frequency. It has a so if there is only a single frequency, so the frequency like in this course we will use nu. So sometimes it's you use f, sometimes you use omega, which is 2 pi f. There are different kind of notations that people use. In this class, we'll use nu. So this looks like a letter V, but it's kind of tilted. So this is the Greek alphabet nu, which we will use for frequency, which is in hertz or cycles per second. Okay, so for monochromatic means wave of a single color. Wave of a single color means wave of a single frequency. Okay, so for one color, light of one color, there is an amplitude and there is a phase. Okay, so the amplitude is this, basically how high this is. This is the amplitude, and then the phase basically tells you what is like relative to this some origin, like what is the, how much of an angle has increased, like as time propagates, or as in function, it could be a function of space or a function of, if it's a function of space, it could also be a function of time. So there is so this is a complex number, and you have an amplitude and an angle. So as you can see from here, this like A is an amplitude, phi is a phase. Therefore, you can represent this as a vector, which has a real part and an imaginary part. This is a complex number, and so this is the amplitude. The angle that this makes with respect to the real axis is called the phase. And as a function of time, this complex number is rotating in the complex plane at certain number of times per second. Okay, so some number of counts, which just corresponds to nu times per second. It's rotating, and that corresponds to an angle. So one circle means 2 pi radians of angle, right? So it's accumulating an angle, which is the phase angle. Okay, that's the basic idea behind this. And so the wave function can be written. There are different ways of writing the wave function. I'll show you a few of them. There's an equivalence between them, and I'll show you what show you the different forms of writing the wave equation. Okay, the wave function. So if the wave function is written in this form, this is what we, so this is a pure, like, so there's A of r, and there is a cosine of 2 pi nu t plus phi. Okay, so there is amplitude and a phase, and then there is a, this is the time, so this is the time variable, these two are the space variables, right? So you can see from this equation that it's a function of, so it's a function of r is space. Whenever you see the letter r, think of it as x, y, and z. Okay, so the, or x, y, z. So basically, it's, or r is space, t is time. So it's there is this function changes at different positions in space and for different time instances. So it is something which is oscillating as function of space and time. So this can also be written in a slightly different way. This is called the complex like amplitude. So this can be written as, instead of the smaller, so small u, if you use capital U, u of r comma t can be written as u of r times e to the j2 pi nu t. So notice that, so basically this, what we have done is taken this and converted it to this. So this is a real number, this essentially becomes a complex number. So why are we complicating things, going from real numbers to complex numbers instead of going the other way around? There's a good reason for that. This way of writing the wave function happens to be extremely useful for most understanding most real world for most real world applications. And so, like, you can deal with this kind of a complex. I'll show you, I'll give you some examples of how this is useful in a minute. But if you know this, then by taking the real part of this, you can immediately go to this. Okay, so that way these can be converted from one to the other. It turns out that this way of writing the wave function happens to be very, very useful. One of the useful things you can see directly from this equation is, so it's u of r times e to the j2 pi nu t. Okay, so this is function of both space and time. It's decomposed into something which has space and something which has time. It's separating the space part and the time part. So the time part, if it's one frequency, it's always just rotating complex number. So you can basically ignore the time component and only deal with u of r. Here the problem is there is a of amplitude of r and phase of r, and the time, phase and space and time are completely interconnected and intercoupled. So it's very hard to kind of separate them in this equation. But if you look at this equation, you can simply, for the purpose of kind of solving most problems, you can just ignore the right hand side. U of r comma t becomes just u of r. The time component is just an oscillation at some frequency, and therefore it's much easier to deal with this second equation than the first. Okay, so that's the that's the basic idea. Sorry, that's small. Yeah, okay. Now, so this u of r here can be written as a of r times e to the j phi of r. So the space components has an amplitude and an angle. So basically this. So if you combine combine this equation and plug it into take this and plug it in here, you will get a of r times e to the j phi plus e to the j omega t. And if you if you take the real then if you take the real part of that, you will get cosine, right? Take this, put them together, take the real part, you will get your answer. Okay, so these what I'm trying to say is these two are interconvertible, and it's dealing with this is much easier, as you will see, and therefore this is what is used most commonly. Okay, yeah. So the other thing is the wavefront satisfy the Helmholtz equation. So this kind of equation. So basically, the capital U that I mentioned, this equation over here, this function over here satisfies the Helmholtz equation. What it means in practice is that, so you have uh, the wave function here can be related to U of r. So the intensity can be is U of r square, which can be related to 2 times U of r square here. So this, the factor of 2 that came in a few minutes ago basically comes because of this. So capital U of r square is the small u of r, twice small u of r square. Why is there intuitively? There is a cosine part and a sine part, right? So the cosine part has half the energy, sine part has half the energy. So if you add the two, it will be double the energy, and that's the reason why there is a factor of two. So, yeah. Mm-hmm. Yeah. Mm-hmm. Sure. So yeah. So if you plug this into this equation, Helmholtz equation, and simplify the two like omega equal to 2 pi nu, the like you will, like if you just plug this equation in to the Helmholtz equation, it will simplify to this. Okay, that's how you get to that. Okay, so this k is the constant. Like, so if you're different, imagine if you're different. So if you have e to the j 2 pi nu t, right? So if you differentiate this twice with respect to uh, t, what will you get? Square, right? So sure. So j square is minus 1, right? So minus 1 2 pi nu square. Okay, so that's and 2 pi nu by, there is a c over here, right? By c square. So 2 pi nu by c. So that we call it k, and you see how it goes. Yeah. So basically, that's how you get this omega by c, or 2 pi nu divided by c. Okay, so basically, so if you solve this, you get yeah. So the the places where phi is a constant is called the wavefront. So let me try to give you an intuition as to what's happening over here. Okay, so let's say there is a wave which is traveling in some direction. So over time, basically it spreads in some way. Okay, so this wave has a certain equation. Yeah, sorry, you can't, can you see there is a red color? It's sorry, it's hard to see. Okay, let me try to, yeah, so let me try that again with a different color, which is easier to see. Okay, so you have a wave which is basically traveling in a certain direction. Is this better? Okay. So over time, this wave is traveling like in this particular direction. Okay. So the places where phi is a constant will be some kind of a shape. It will have some kind of a three-dimensional. It's a plane of some sort of like a curve of some sort in three-dimensional space, and that moves. It this like after a few like small amount of time, the like this would have traveled. This is if at one point in time it's this shape, like a few, say, 1 nanosecond later or something, it would have shifted a little bit to the right. Okay, and over time, so the place where the face is a constant, all the points in space, if you connect all the points in space where the face is a constant, that will have a certain shape, and that shape moves in some in over time. So that this all the places where this is a constant is called the wave front. Okay, so that's the idea. Maybe if you connect it to how many of you have heard of the Huygens principle? Like this was from like 11th and 12th perhaps. So basically, what Huygens said was that let's say you have like if you have a wave which is traveling, take any point on that wave, think of it as emitting a wave itself. Take another point, it's emitting another wave. Take another point, it's emitting the wave. You add up the contributions of all of these waves, they will have some kind of a shape. So this shape, this slowly travels over in space. So this, like all these points, what they have, all these orange color points, what they have in common is that they have the same phase at some point in time. So basic, and then and this is another like curve which has all points on that curve have the same phase. Okay, and that's called a wave front. That's the idea. So basically, phi of r is equal to constant defines the wave, what's called the wave front. Okay. So in summary, so what starting with the postulates of wave optics, what we have said is that for a monochromatic wave, meaning wave of one color or one frequency, it can be described by a complex function, a wave which is of this form, which satisfies the wave equation, and the complex amplitude u of r. So you just take this part, ignore this part, and only take the u of r part, satisfies the Helmholtz equation, and its magnitude and angle are called the amplitude and phase of the wave. Okay, and the intensity of the wave is the amplitude squared, and the wavefronts are like the wavefronts of are surfaces of constant phase. Wherever, if you connect all the points which have the same phase, that constitutes the wave front, and that's phi of r. And the wave function, which is small u of r of t, is the real part of the complex number, which is real part of u of r comma t, and this also satisfies the wave equation. This is really a kind of whatever I said in the past few slides. This kind of essentially encapsulates all you need to know about. Starting from the postulates, we get to this point, and from here we build out like our understanding of wave optics. Okay, yeah. Mm-hmm. Yes. No. First, phi r. Yes. Phi r is the definition of phi r is argument of u. It's not an equation in like sort of. This is the definition. Yeah. Sure. Correct. So phi r equals constant is will give you one wavefront. For a different constant, it will give you a like different. Yeah. So yeah, different phi r equals constant is if you solve, it will give you the shape of the wavefront. Yeah, that's right. Okay. So now starting from this point, so like there are different kinds of waves. Okay. So we'll start with the simplest version of a wave that can travel, which is called the plane wave. Okay, so basically a wave. So the thing in optics is that you have to imagine in 2 and 3 dimensions, which can in the beginning can be a little bit difficult. But I hope as we go along, you try to get an imagination. Like I'll show you some animations and stuff which could help. But in the end, you need to imagine in 2-dimensional space or 3-dimensional space, which like sometimes is a bit difficult. But like I'll try to help you and stop me. And if you have some difficulty understanding something, please stop me as we go along. Okay. So the plane wave can be written in this particular form. Okay, so some amplitude times e to the minus j times k dot r. Okay, so it has kxx, kyy, kz, z. So this is the equation of a plane wave. So what it looks is probably more important for us. So basically it has maxima and minima, maxima and minima. So basically there are a bunch of maxima and a bunch of minima over here. So it has ups and downs, ups and downs, ups and downs. And over time, this travels, in this case, to the right. Okay. There is a wave front. So to illustrate this, maybe this is a bit easier. So it's a sinusoid of some sort. Then it over time it travels in a particular direction. Okay. So this is basically how a plane wave moves. And the equations that we write typically describe the nature, how the wave is propagating in space. Okay, so for a plane wave in any medium, if you think of it as a monochromatic wave, meaning wave of one color or one frequency, it propagates through a media of different refractive indices, and its frequency remains the same. Okay, so what I'm saying is, start with this. So this is traveling in air. Let's say it enters a medium, okay, a glass or something of that sort. Then it slows down, and what is and what doesn't change is. So what happens to the wave is that the frequency is constant. Frequency does not change, but the wavelength can change. Some of the other properties of the wave can change, but what does not change is the frequency. And this is true in general in most of optics and even for most linear systems. There is one principle which is interesting and useful. So you might remember that. So the thing that is crucial in any system is the invariant, what is called the invariant. Say, for example, in Newtonian mechanics, momentum is the invariant. Momentum before something happens and momentum after something happens is the same. There are a lot of things that can change this. Velocity, this, that, mass, things can change. But the momentum before and after is invariant. Okay? And then same thing with energy. And some sort of energy before and energy after are the same. So that's an invariant. So many things can happen. Like something could be burning, some complicated things will happen. But that which does not change is a crucial component of any physical system. What I'm saying is, in optics, frequency is an invariant, meaning if as waves travel and go from a place A to B, the wavelengths can change, some things can change, but for most kind of linear, what are called linear systems, the frequency as it travels from one place to the other is always the invariant. It does not change. And that's a crucial parameter. Yeah. Mm-hmm. Yes. So K is a, let me write it with a different color. It is a vector, yes. So this K is in bold is a vector, which is whose is Kx x hat plus Ky y hat plus Kz z hat or z hat. Okay. The magnitude of this vector K is equal to K equals omega by c. Okay. So this K is called the direction vector. I'll get to that in the next slide, but so K in this case is the direction in which that particular plane wave is traveling. Okay, and xyz, so K dot r. So K dot r, if you take the r is x hat plus y hat plus z hat, right? So if you take the dot product, you will get kxx plus kyy plus kzz. Okay, so that's the dot product of two vectors. And what we are saying is that if the k tells you the direction in which the plane wave is traveling, that's the direction vector of the traveling plane wave, and x, y, z is space. Okay, so if you take the dot product, then that's the direction in which the wave is going. Yeah. So when if the wave travels into a medium which has some refractive index, c remains the same, but its velocity could change, its wavelength could change, its wave number as defined here could change. But so okay, so this is the this defines the refractive index. What happens to the wavelength? Wavelength actually becomes smaller. So if a wave is traveling in air, it goes through glass, then the wavelength gets compressed. It becomes smaller. And how much does it get smaller by? The factor of refractive index. Okay, if the wavelength is 1 micron inside in air, if it goes into something which has a refractive index 2, it becomes half a micron in wavelength inside the medium. That's the basic. That's how it will work. Okay. Yeah. Any questions so far? Sure. Mm-hmm. That's yes. So that is the good thing. That's the usefulness of the U of R. So the reason, one of the reasons why we went from small U of R to the complex U of R, right? This the capital U R. You separate out the space term and the time term. And the time is e to the what is the time term? E to the j 2 pi nu t. So nu is a fixed invariant. Therefore, it's like before going to the into the medium, after going into the medium, nothing, it does not change. And time is an independent variable. So basically, because nu is an invariant and like it's just like there is one rotating term, complex number, you can separate it out and ignore it and do all your calculations with using u of r without worrying about time, and at the very end you multiply by e to the j 2 pi nu t and take the real part and you'll get your answer. So that way, like that's one of the simplifications that this complex numbers notation allows you to do. In this particular example, in fact, what happens when you have different wavelengths, we'll discuss that. What happens in other situations, we will discuss that. But we are starting with the simplest kind of wave, which is one frequency and which is one going in one direction. Okay, in fact, in the next few slides, we'll look at a few other different examples. Yes. Yes. In this particular case, purely for mathematical simplification that we use complex numbers, it turns out that if you go to quantum optics, the wave function itself is fundamentally complex, meaning you cannot take the real part and do any calculations, or the world is inherently complex in the quantum mechanical world. But in this classical world that of wave optics that we're dealing with, the complex numbers is purely a mathematical like for mathematical convenience and mathematical simplification. That's a good question. Yes, in this case, in like yeah, in everything to do with this kind of optics, wave optics, is mathematical simplification. Any other question? Okay. All right. So the next kind of another type of wave is called a spherical wave. Okay. So a plane wave is and remember that a plane wave is infinite in all different directions. So it's infinite in all directions, and it's traveling in a particular like in a direction, and the direction is defined by the direction vector k. Okay, so the k vector here tells you the direction in which it is going, and it's infinite in all directions. Okay, so another kind of a wave is what's called a spherical wave, where let's say you think of one small point which is emitting light, and that it's spherical in all different directions, and the light is getting emitted and it's traveling from the middle in all different directions. If you take a cross section, it will look like circles which are expanding one after the other, but it's actually in 3 dimensions. It's like spheres, one bigger than the other, bigger than the other, kind of like that. So this is, and the equation for a spherical wave is given by u of r, which is a naught divided by r e to the j kr. Okay, so let's k. Look at this is a scalar k times, and r is the radius x square plus y square plus z square square root. Okay, r here is x square plus y square plus z square square root. Okay, so k is so this is an equation. Let's think about what this means. Okay, what we are saying is that when you have a spherical wave which is expanding, as you go farther and farther away from the middle, the amplitude becomes lesser and lesser. It's dying out. Why is it dying out? Because energy is spreading out. Therefore, its amplitude is becoming lesser and lesser as you go farther and farther away. And what else is happening? In going any direction, independent of the direction, it's accumulating phase. The phase is increasing from the middle. Whichever direction you go, it only depends on the radius. So, if you have take one point here and here, just calculate this radius r, and every point, like, sorry, I didn't draw it properly, but basically in that radius, all the points have the same phase, and so basically the wave front is a sphere, where the phase is a constant, basically a sphere. So what we are saying in this equation is that the amplitude of this spherical wave is reducing as it becomes bigger, and the phase is accumulating as it travels away from the center of the sphere. That's the nature of spherical waves. Yeah. That's an interesting question. It has to be 1 over a naught by r alone, because of law of conservation of energy. So a naught by r, right? It's expanding as a function of r. Intensity is u of r squared. So intensity will vary as 1 over r squared. And so let's take any sphere of some radius, right? The total amount of energy, if you calculate, what is the surface, like over the entire surface? It's 4 pi r square is the surface area, right? Surface area times this amplitude, 4 pi r square times r square, the r square cancel, and it will become a constant. So the energy in any sphere will always be a constant. If it was 1 over r cube, then the energy would be decreasing as a function of space, which violates conservation of energy. Therefore, it has to be 1 over r. So this is Correct. So this is in free space. So therefore, in free space where there is nothing else around, energy cannot be so. If there is a material where there is which is absorbing energy, some atoms or molecules which are absorbing, then you can have damping in the medium. But if this is the case where there is free space, there is nothing which can remove that energy. Any other questions? Okay. So this is this is how you think about how the wave travels. Starting from the middle, the amplitude, so it's in a way it's dying out, and the phase is increasing as you go along. This red circle is basically the wave front, or the point where the phase is like all, if you connect all the points where the phase is the same, it will be the red circle or the blue circle, the maxima or minima, and that is traveling outwards. Okay. So yeah, in order to, so the plane waves and spherical waves are kind of the two most common. These are the solutions to the wave equation, and they are the most useful kind of simple wave, simple functions. The way we will think, like the way to think about any general shape is as a combination of plane waves and or spherical waves. That's really, so where we are going in the next few slides is, so any complicated wave can be thought of as a combination of plane waves in different directions or spherical waves in different directions. Okay, so this is in a way like what's called the plane decomposition or angular spectrum decomposition. We'll get to that in the next few slides. But what I'm trying to, that the basic takeaway message here is that, so you have simple plane waves. If you have a very complicated wave, you can think of it as a combination of these plane waves, a linear combination, meaning addition and subtraction, weighted addition and subtraction of these plane waves. Or alternatively, you can also think of any complicated wave as a linear combination, addition and subtraction of multiple spherical waves at different positions. Okay, so that's basically the like those are the kind of ideas that we are using in the and I'll go into the math and then some more details of how exactly to do that. So like in terms of equations. But what I really want you to take away is this mental picture that any wave can be thought of as a combination of plane waves. So if you understand a plane wave, you understand a spherical wave, you can add them up and understand any kind of wave. And that's something you always need to keep in mind. Okay, so how do we get to that? Okay, so let's take a spherical wave, and spherical wave has this like, yeah, so you have xyz in this, right? So basically, let's say you have a situation where, so r is x square plus y square plus z square root, right? So let's make the approximation that square root of x square plus y square is much less than z square. Like, why is that? A scientist by name Fresnel, who was a French physicist and mathematician in the mid 1800s, came up with this. And so basically, what we say is that R is like, if you do this, if you use it like do this and take a Taylor-Maclaurin series expansion, you get something like this. If you take the first order approximation, like you'll get this approximation. Sorry. And so R in this wave equation, spherical waves, can be written as z plus x square plus y square by 2z. Okay. Therefore, u of r will become this amplitude times e to the k times z times e to the, so basically this term. Yeah. So what was u of r previously? It was this, right? So what I'm saying is that u of r, which was a divided by r times e to the as k r. For r, if you substitute this, then you simplify a little bit, you will get this equation. Okay, so what does this mean? You get some equation, like what's the point? Like, you need to think about what any particular equation means. What it means is that, of course, the amplitude as you go. So take this example here. So this is the z direction, right? Like this direction. Let's travel along z. And what happens is that as you go like farther and farther away, the amplitude again decreases as 1 over z. Then the phase changes as e to the kz times z, or k times z. And then there is what this extra term. So the phase has this particular shape. So if what is, like, if you remember from your coordinate geometry, what does this represent? It's a circle, right? And in this case, it happens to be c equals 2z. Okay, but so if this is a constant, if the face is a constant, so this is the face part. If you equate the face to be a constant, like it will be in 3 dimensions, it will be a spherical surface, right? So it's basically what we are saying is that it can be approximated by a sphere, like a sphere. The wavefront will be spherical in nature. The amplitude is 1 over r, and then is accumulating a phase which is e to the k z k times z. Okay, so yeah, so here is basically what we are saying. So this can be interpreted as the spherical. So the spherical wave is traveling along z. In this region, the as it goes along, the amplitude is reducing by this factor here. It's accumulating a phase by this factor, and it has this shape, which is the spherical or circular shape of this. So, okay, so that's the Fresnel approximation. It's so we can connect these. Sorry. So so y square equals 4ax is a parabola, right? So it depends on how you x square plus y square equals 4ax is a parabola in that sense. Okay, so there are, if you look at it from different cross sections, it'll, like, if you take a cross section, it'll look like a circle. But if you look at it from the other direction, if you look at it from the xz cross section, it's a parabola. If you look at it from the xy cross section, it's a circle. You get what I'm saying? It's in 3 dimensions. That's where, like, you need a little bit of imagination. So if you, it's a parabola in this direction, but if you take a slice like this and look at it from the side, it'll look like a circle in this direction. Okay. Okay. So let's get back to, yeah. So the other thing about these kind of spherical waves under this approximation is that you can connect this to ray optics. As I mentioned in the beginning of today's lecture, like, ray optics is a subset of wave optics. And the way to think about rays is, a ray is I'm sorry. So if this is one wavefront and this is another wavefront, rays are perpendicular, like lines which are perpendicular to this wavefront. So rays of light are going like this, and that means the wavefront is basically in this direction. Let me use this different color. So if this, so if the wavefront is like this here, the rays would be going perpendicular at any point. It's perpendicular to the wavefront. Okay, so this connects wave optics and ray optics. So whenever you have a wavefront, you can draw perpendicular at any point, and that's the direction of the ray. Okay, that's one way to think about rays. And the other thing is that the rays which are very close to the z-axis here, which are close to the optical axis. Remember from last time we had the lens equation, and we said that the lens equation is only correct when the rays are very close to the z-axis, traveling very close to the z-axis. So paraxial waves means they are also, the wavefronts are almost perpendicular to the z-axis. And they are kind of, in other words, the rays are very close to the almost parallel to the z-axis, and therefore the wavefronts are almost perpendicular to the z-axis. So those waves which are traveling in this way are called paraxial waves, and these are very useful. Like, just like with the lens, So whatever we derived for ray optics in terms of the lens equation, that 1 over u plus 1 over z1 plus 1 over z2 equals 1 over f, right? Like that kind of an equation is also true for wave optics. In the wave optics picture, the same kind of thing is also true. So here is an example, another example. So basically, if the wave is, if the rays are going like this, then the wavefront is perpendicular to it. So this is the plane waves. So whenever you draw ray optics, you draw parallel lines, and in wave optics, that becomes kind of plane wavefronts traveling in one direction. Okay. Similarly, for spherical waves, you have rays going from the one point away in all different directions, and that is equivalent to, in wave optics, the wavefront going away in all different directions. Okay, so there is this important connection between ray and wave optics. Similarly, for the lens case, last class we derived the lens like equations for lens. So if you have a parallel rays of light coming in and falling on a lens, what happens? It focuses to a point, right? We saw that in the last class. So basically, we can use the same wave optics picture. Wavefronts are falling, a parallel set of wavefronts. A plane wave is falling on a lens, and it becomes a converging spherical wave, and it converges to a point. Okay, so basically, you can go from ray optics to is an equivalent picture in wave optics for every one of the phenomena we see in. This is true for paraxial rays, and in this case, paraxial waves. Okay, so everything that we have learned for ray optics is directly related, like kind of transfers to wave optics. Additionally, there are some new things which we'll also, the second part of today's lecture, will like what are the new things? Why, if rays work so well, why do we need waves? There are some phenomena like interference or diffraction, which like that does not happen in ray optics. It only happens in wave optics. Okay. Another example of is reflection. You remember last time, light fell on the mirror, rays of light fell on the mirror, angle of incidence was equal to angle of reflection, light got reflected. In this case, you have a set of waves traveling, falling on the lens, and the waves kind of getting reflected. The wavefronts get reflected. So this is the wave optics picture of how light reflects from a mirror. So we saw how the wave optics picture of how light travels through a lens. This is the wave optics picture of how light travels and reflects from a mirror. This is the wave optics picture of how refraction happens. So remember in the previous case, we had a ray of light falling, and it like n1 sin theta 1 was equal to n2 sin theta 2. We had that picture, right? So in this case, notice that there is a certain wavelength, and there is a, like, look at the wave on this side. It's hitting a boundary, and what is happening to this particular wave? It's changing direction. The direction vector. So the k, initially there was a direction vector k1 in which the wave was traveling. So this is perpendicular to the wavefront, right? So k1 is the direction vector of the incidence. The direction vector after refraction is k2. The direction vector became from k1 to k2. What else has happening? The wavelength, as you can see, this has become shorter inside the medium, and it's compared to outside the medium. The wavelength has become shorter. And how much has it become shorter by? N2 by N1, ratio of N2 by N1. That's how much the wavelength has become compressed. And so this is, and again, and this is equivalent to saying lambda 1, lambda 2 by sine theta 2 equals lambda 1 by sine theta 1. And so this is the equivalent of Snell's laws in the wave picture. Like I didn't say it right, but like you get what I'm talking about. Okay, so this is the angle theta 1. This should be, yeah, and this is the angle theta 2. Okay. Sorry? Okay, yeah. If you have another medium, say, let's say you have another medium here, and it can change again, and so on and so forth. So this is true for any number of like multiple media in between. Okay. Yeah. So, and what happens if you have um, so in terms of pictures, I'm trying to show what you can like what you should imagine in the wave. Like, so in terms of rays, I think you can all imagine how light reflects or refracts. I'm showing the wave picture of thinking about light when you have refraction, reflection, and so on. This is where, like, let's say you have just a thin piece of glass, and light comes in perpendicular to it, and what happens? If in the ray picture, just light simply keeps going through. But in the wave picture, the wavelength, there is something that changes. What changes? The wavelength changes. So inside, outside in air, there is a certain wavelength. Inside, the wavelength becomes smaller. And again, after it gets out, again, the wavelength becomes bigger. And it continues to travel. And the equation for that would be, so here, like, e to the minus j n k naught, yeah. So basically, the amount of, yeah. So it accumulates a certain amount of phase. Just air, it would accumulate e to the minus j k naught d. But because it's going through a medium where the refractive index is n, it will become n k naught d. So there is this extra term here, right? So there's an extra n term in this equation, which is basically, it means that it is getting compressed. Like, so instead of the distance, even though the physical distance here is d, it's as though optically it has traveled n times d. It has traveled some extra distance. The light appears as though it has traveled this extra distance n times d instead of just d. Yeah. So instead of it falling perpendicular, what happens if you tilt it and it goes through the glass? Where wave comes in, it tilts a little bit, it changes direction a little bit. K vector k becomes k1, and it becomes wavelength is shorter, and again it comes back. So these are parallel to this. So the direction here and in and out is the same, which is k, but like this is the shape of the wavefront inside the medium. Okay. Same kind of thing happens inside a thin prism as well. So if the direction vector k becomes a different direction vector, if this is k1, it becomes k2, direction vector k2, if it goes through this glass which has a certain angle. So what does a prism do? It changes the direction of light. Excuse me, sorry. Changes the direction of light. Yeah. So one of the assumptions we have made in the ray optics as well as in wave optics is that assume that the lens is thin. Okay, so it's fairly, like, the thickness of the lens is basically typically ignored, and that way we can kind of assume that, like, the lens is as though it's in the middle point, some point somewhere here. So wave is coming, hitting this, essentially this boundary, and before that it is a plane wave, after that it's a spherical wave. So that is assumption. So this kind of what happens in this region we are ignoring for the purpose of so the equation that we have derived assumes that, like, we are not using bringing our, like, imaging system very close to the lens. When you bring things very close to the lens, things don't work like as predicted in the theory. So that's why we do, like, this is assumed to be very thin. So whenever you're using a lens equation, assume that Z1 or Z2 cannot be very small. Okay, they have to be compared to 1 over f. They have to be reasonably big. Okay, reasonable. Those are approximately like numbers. Okay, yeah. Mhm. Sure, sure. Um, that's an interesting. There are different ways to imagine that. Okay, so take this direction vector. Okay, k. Okay, so now basically what we are saying is that the like let's start with something which has only one direction, right? Like let's say you have x, y, and z. Okay, and the direction vector k is going like this, right? So so let's take if it is just along z, then what is k dot r is just kz. It's only one direction. So so basically kz times z, kz times z. Okay. So basically, phase is accumulating only along this direction. So what we are talking about is the accumulation of phase. What in what direction is the phase accumulating? So you're taking the direction vector and projecting it along x, projecting it along y, projecting it along z. What we are saying is, if you travel along x, this much phase is getting accumulated. If you travel along y, this phase is accumulated. If you travel along z, this much phase is accumulated. The overall phase accumulation is how much along x, along y, along z. You add the three up. That is the overall phase increase as you travel in that direction. That's what we are saying. So e to the I of j k dot r is the same as e to the j kx x times e to the j ky y e to the j kz z. Okay, so this is the phase of how much phase accumulates along x direction, how much phase accumulates along y direction, how much phase accumulates along z direction. So so the overall phase. This is essentially what this is one way of interpreting this. There are a few other ways as well, but like that's the basic idea. Okay. Yeah. So same. So in the wave optics picture, so this is the ray optics picture where parallel parallel rays are incident on the lens and they focus to one spot. So if you have any general point in the ray optics picture, light rays come out from this point and they focus onto another point, right? So 1 over z1 plus 1 over z2 is 1 over f, the lens equation. In the wave optics picture, basically light, it's a point source is emitting light, it hits the lens and then it converges the light back to another point. So that's the wave optics way of thinking about what the lens does. Any questions so far? We'll take a break soon. Okay, just give me a few minutes. Yeah. So the next kind of device or object that we think about is what's called a diffraction grating. How many of you know what a diffraction grating is? Correct. Yeah. So yes, it could be slits. That's practically yes, that's true. But it's something like a sinusoidal. Take a piece of glass, and if you have a sinusoidal pattern on that glass, then that is a grating. And what a grating does is takes a plane wave and changes the direction. It sends it forward just like if it was not there, but it also changes. It sends from one plane wave. It creates multiple plane waves in different directions. Okay, So this is, and in fact, the angle is like the directions in which it sends are very specific to the grating. We'll get to what exactly that is a little later. But basically, it takes one plane wave and splits it into multiple plane waves in different, very specific directions. And like one of the things where it's used is the different colors. This grating change sends like so splits the colors, blue, red, and green, and so on. It splits the colors, and that's one of the kind of uses of this kind of a grating. So the other thing I wanted to mention was that, so in a lens, you have this kind of a shape, right? So lens is a glass which has like two surfaces which are kind of curved surfaces. Equivalently, you can, instead of using a different shape, you can have a rectangular piece of glass, but change the refractive index. You have higher refractive index here. As you go farther away, you make the lower refractive index. You can achieve the exact same effect as a curved surface. And so, in fact, you can make this refractive index gradient takes a plane wave and it converges the light to a point. And this is what's called a graded index optical component. So people have made lenses, what are called graded index lenses, GRIN lenses. So it's like where light is incident, it does focusing. Instead of it being a curved surface, it will actually be two flat surfaces, but the refractive index inside is changing. So this is another way of, so whether it's optic, so you can think of how much of optical length this is, right? The optical distance here is big in the middle, it's smaller at the edges. So if your refractive index is high here, the optical distance is big in the middle, optical distance is smaller away. So as long as the optical distance is varying, just like in the curved surface case, if you have the same profile, you will have the same optical light will also converge just exactly like it would. Okay, so these are another type of components. In fact, you can, it's not as easily available as regular lenses, but we can buy them, and it's very useful for certain kinds of experiments. Okay, so the next kind of topic I wanted to cover is interference. So this is where ray optics breaks down. You cannot think of light as rays, but you have to think of light as waves. So what does that mean? If a ray of light and another ray of light are going next to each other, the ray optics, there is no way of combining these two rays to say something about what happens, what is the like kind of, if you put a detector there, what do you measure? But like when you have waves traveling in one direction, waves traveling in a slightly different direction, they combine, they linearly add, like the principle of principle of superposition. You add the two waves. In other words, you add u1 of r and u2 of r. You add the two, and I told you that the process of making a measurement of light is equivalent to finding the intensity. And when you find the intensity, you take magnitude square. That's the definition of intensity. When you take the magnitude square, you have u1 plus u2 square. So you will get u1 square plus u2 square. So this is the intensity of the first one alone. This is the intensity of the second wave alone. But there are these extra terms which are what are called cross terms. This is where interference happens. These are the terms because of which interference happens. So you have I1 and I2, which are the intensities of the individual light. Then you have these I1, I2 cosine of phi. So basically, this is the phenomenon of interference. The two waves interfere with each other, and you will get like bright and dark patterns in the that you can detect, which is so the intensity, overall intensity that you measure will be which will have ups and downs. So there will be some constant offset, and then there will be up and down depending on the values of the phase difference between the two waves. Okay, so how do you use this interference? So there are different what are called interferometers, which explicitly use the concept of interference and makes use of the wave nature of light to build imaging systems. In fact, there are, I'll talk about a few different configurations. So what happens here is, this is what's called a Mach-Zehnder interferometer. What happens is, light comes in. This is a beam splitter. This is component. It splits the light into two pieces, and it reflects. This is a mirror which reflects light. This is a mirror which reflects light. Here again, it's a beam splitter or a beam combiner. So after this beam and the reflection of this beam and the transmission of this beam, they combine with each other, and there is interference here. Same thing. So I'll use this color. Green here goes through here, and the blue here reflects here. So the reflection of one and transmission of the other. The green and the blue interfere with each other. This is a way of taking two beams, combining them, and intentionally creating an interference pattern. Okay, and if you measure the intensity either here or here, it have this kind of a profile. Okay, as a function. So it depends on the distance. The distances here and here, and distances here and here. So depending on the difference in distances, there will be a different intensity pattern as a function. Okay, so this is called a Mach-Zehnder interferometer. The more common one, which is some of you might have seen this, so it's called a Michelson interferometer. So Albert Michelson, who was late 1800s, early 1900s, he got the Nobel Prize for this interferometry. So basically, in fact, so what happens here is that light is sent, it splits into two. Okay, let me use different color here. Okay, and light goes and comes back here, and this light reflects, and part of it transmits, but we are not interested in that. So this light comes in here, reflects, and whatever transmits, the blue and the green interfere with each other. If you put a detector here and make a measurement, you will, so there is a certain distance here, there is a certain distance here. If you move the mirror left and right, then you can measure as a function of that movement, you can measure this intensity pattern on the detector. And so this is the equation. So this is called Michelson interferometry. It turns out that this kind of interferometry is one of the most useful for making medical devices. I'll devote an entire lecture to this at a later stage. The instrument idea called optical coherence tomography, and that is used to get three-dimensional information about the inside of objects on a small microscopic scale. Okay, and that uses a Michelson interferometer. You have a mirror, and instead of here having a second mirror, we will actually have the body, like some region of the body. Light is incident on the body. So in this configuration, light comes back. Look at the interference of light. Put a detector. There is a little bit more to it, which we'll get to, but I'm just explaining the basic idea. So basically, using interferometry, using the wave nature of light and combining kind of light to splitting it and then recombining it and making interference and detecting, you can get three-dimensional information from inside objects. And exactly how that works is something we will discuss in much more detail. Okay, and then another kind of interferometer is called a Sagnac interferometer, where light comes in here, split in two. One goes in this counterclockwise direction, clockwise direction, other goes in the counterclockwise direction. Both come out the other end, interfere, and again it's the same principle. So you split. So in all these kind of interferometers, you split light, then recombine them afterward. After one goes through one path and the other goes through something slightly different. So the difference will create the interference. And so what is the difference between one path and the other path? In this case, it looks like there is nothing here. But imagine if you put an object like sort of, or let me take this. Let's say you put an object here, right? So like something is happening in one path that is not happening in the other path. The interference creates a very sensitive way of finding the difference between the two, what is happening in the two. And the difference is measured through the interference pattern. And whatever is the difference, that's what that's the thing that we are interested in figuring out. Okay. So yeah, if you have interference of two oblique plane waves, meaning there is one plane wave which is going in this direction, another one which is in a slightly different direction. If you put a array detector here, what do you see? Or just a screen like what do you see? You see a diffraction pattern. Basically, it looks like this. And this, in fact, might remind some of you of what's called a Young's double slit experiment, where you have like there's one hole here and another hole here, and like so get it from one angle, like this a spherical wave is emitted in all different directions from this one. Spherical wave is emitted here. When they interfere, there is a light and dark, light and dark, light and dark pattern that you will see. This is the interference pattern. Okay, let me take a break right now. We'll continue this. Yeah.